Qué pena que estamos un poquito tarde, pero no está tan grave. Bueno, es un placer tener hoy a David Hernández, que viene de coinvitado con astrofísica en la Católica. David es un astrofísico teórico y computacional. Pertenece en este momento al Instituto de la Teoría de Computación del Harvard-Smithsonian Center for Astrophysics, que es el CFA. Obtuvo su pregrado en la universidad, debería decir, tal vez debería hablar en inglés porque David me estás entendiendo todo.
Sí, yo entiendo. Adelante.
Ya. David obtuvo su pregrado en la Universidad de Arizona. Y el doctorado en MIT en 2018. También tuviste, esto fue durante el doctorado que tuviste el fellowship de Lyon.
Fue el doctorado.
Es durante el doctorado, fue un fellowship de MIT Lyon. Y su tesis fue supervisada por Bertschinger. Desde su doctorado, David ha tenido posiciones postdoctorales en MIT, en el Centro de Astrofísica de Harvard-Smithsonian, en Riken CSS, ese no lo conozco.
En Japón.
¿En Japón?
Sí.
En Japón. Y otra vez en el CFA. Y ojalá pronto en la Católica también, ya como profesor. Bueno, entonces la investigación de David se enfoca en el problema de N cuerpos, el N-body problem, que describe el movimiento de los planetas y las estrellas, y hoy nos va a hablar un poco sobre los aspectos computacionales de este problema. Entonces, por favor, recibamos un aplauso.
Sí, I'm going to speak in English because I haven't given scientific talks in Spanish. Pero encantado de estar con ustedes y quizás hablar un poco más con el que quiera. Okay, so yeah, let me start with my conclusions. Oops. I don't think anything. Okay, so let me start with my conclusion slide. So I'm first going to talk to you about how symplectic and time reversible numerical integration helps us study the solar system and other problems in astronomy. I'm going to try to convince you that this question of solar system stability, this is a very old question, very studied by many authors, is affected by numerical chaos. And the effect of numerical chaos is to overpredict the instability of the solar system. I'll show you how that happens. And also talk to you about various tools, gravitational tools I've worked on that can be applied for various problems. One is the so-called transit timing variation problem. So I'll explain what that means. I also want to mention this talk will be a little bit at a high level overview. I won't get into very technical details, but if you want to know technical details, I'm very happy to discuss and questions or whatever. But I'm trying to keep this a little bit more general. Okay, so let's talk about the solar system and specifically minor bodies, which include asteroids and comets, and how we might use symplectic and time reversible integration to understand this problem. First, a little bit of an overview about what the N-body problem is. That's the basic description of the problem we're solving. So an N-body problem was basically first introduced by Newton with his law of gravitation. But we just have N-point particles okay, interacting through some pairwise force. And the question is, you can set up some ordinary differential equations, so solve for the motion in time. This is the case for gravity, Newtonian gravity. It's the case for electromagnetism, for electricity. It's the case for molecular forces. So this problem describes a lot of different kinds of physics that we might be interested in. In astronomy, the dominant force at large scales is gravity. Gravity is responsible for a lot of different structure that we see, and at different scales, because there's no length scale. Gravity has no characteristic length scale. So some of the different structures we have at smaller scales, we have planetary systems. So in this system, we usually have a dominant mass, right? A massive star. We have some planets. The planets usually are in approximately elliptical orbits, okay, nearly Keplerian motion. This gets more complicated. We can have moons. We can have close encounters between the bodies. So the model can get as complicated as you want. Other structures we have are stellar clusters, like open clusters. In this case, the symmetry is spherical. So the orbits are not on Keplerian motion anymore. They're not necessarily on elliptical orbits. This can have a lot of structure at small scales, like hard binaries forming. But we can also have out here in the halo, we have stars that are moving on slower orbits. So you have a big range of length and time scales to worry about that you need to resolve all of them. So the n-body problem is generally non-analytic. So we have to rely on computational methods or some other approximations. Okay, at larger scales, this is a picture of a dark matter halo. In this case, n becomes very large. In this limit, we can treat this problem as a fluid. This introduces a lot of different challenges in this fluid case, because now the particles are just a Monte Carlo representation of the fluid. Okay, so the particles, when they have close encounters, are not real because they're just sampling the fluid. So we have to introduce things like softening. We have to change the force at close encounters. We don't want them to scatter off each other. That's not physical. So we have to do things like change the force law when there's close encounters. There's also a problem of discreteness error.
How large is n? How large? Roughly?
Oh, well, that depends on what the dark matter is. But assuming it's a fundamental particle like, say, WIMPs, this is, it's a huge number, really. Something.
Order of magnitude 10 to the.
I actually don't know the number, but it's bigger than trillions, I guess, more billions, trillions. Depends on the mass, the fundamental particle mass, but yeah, okay, some huge number. So all of these have different challenges, and some other challenges is that the masses are not actually point particles, right? So typically things have size that we can model that as mass moments. We might have other forces which aren't pairwise. We might have drag forces, radiation forces. So you can keep making this model as sophisticated as you want. Then another issue is the issue of long-term accuracy. So the n-body problem is generally chaotic. So this means that slightly different initial conditions are, the difference between the systems are going to grow exponentially in time according to a local Lyapunov exponent. And I don't know if I can play a movie here. Yes. So let's see what that looks like. Here we have two different groups of stars. We have the red on top of a black system. And we're going to use two different integrators, so two different solvers of the Newtonian equations. they introduce slightly different errors. And because of this, we're going to see how after enough Lyapunov times, the solutions are completely divergent. So, oh, this may not work. ¿Es posible hacer? Maybe.
So what program are you solving here?
This is just 3 stars using Newtonian gravity. Starting at rest. What's that?
Can you just describe what happened to us?
Oh, it's totally well, it's chaotic and it's messy. Yeah, okay, it's okay if we can. Okay, so, oh, but it doesn't show.
I paused it, but let me just. Oh, it's not showing up in the.
All right. No, it doesn't work. Okay, it's okay. I'll just talk about it.
Oh, then it works.
Okay, great.
Sorry.
Yeah, no problem. Okay, so great. Let's keep going. Sorry about that. So this is a chaotic problem. So the 2 trajectories, the 2 systems initially start on top of each other, but after enough local Lyapunov exponents, they look very different. Soon they look totally unrecognizable, right? And then we're going to have a final state, which is an unbound system and an ejected star. So here it happens for the black system, and then we have a different time for the red system. So given this, the question is, which one of these are correct? And the answer is, you can just say both of them are correct or neither of them are correct. The issue is that we need to think about this in a statistical sense. So this is something we can't talk about today, but we can look at the statistics, for example, of that final state of an ejected particle. And we can see whether that PDF you construct is accurate. And that's a question we can address. So that's not something we'll talk about today. Let's go back to the.
Sorry, the equations that we're solving, it's a simple n-body problem.
Newtonian gravity, just
Newtonian
three.
gravity. So how does it look like? It's a G times M1 times M2.
They're all equal mass particles, M1, M2 over pairwise distance.
Okay.
Yeah. That's the potential. Okay, so let's talk about the solar system. Let's talk about some of the minor bodies. So there are a lot of families. Some are stable, some are long-term lived, some are shorter lived. For example, we have the Lagrange points in the restricted 3-body problem that give you some stable families around Jupiter. This is the outer solar system with the sun. And we also have, these are called the Trojans. We also have Neptune Trojans. But we have other populations like the Centaurs, which are more unstable. This is because they cross orbits with the outer planets, and the scattering, possible scattering causes this instability. Then we have other things like resonant objects. So resonant, so Pluto is an example. So this means that we have an integer ratio period with Neptune. So the question is, with such a system, how can we try to understand its origin and evolution? So minor bodies are usually on orbits with well-defined length and timescales, but they can undergo collisions with themselves and with with massive bodies. And these are a challenge to numerical methods because we have to resolve these scales. And there's the question of what does it mean to resolve, and we'll get to that. Yeah, what's sufficient resolution? Okay, so usually for this kind of problem, a very successful code is called Mercury, which is a gravitational dynamics code which solves the Newtonian equations and can take care of close encounters. And here are just some recent applications of this code. But let me tell you why this code has been so successful. So here's the paper that introduced this over 20 years ago by Chambers. And here's some citations over time. It's been very popular. So the title of the paper is a hybrid symplectic integrator that permits close encounters between massive bodies. So the key words here are hybrid symplectic integrator that I want to focus on. And I want to explain to you why this has been so successful, why it's really changed astrophysics and other quantitative sciences, this concept. So for our purpose, when we talk about symplecticity, we can interchange it with a Hamiltonian code or map for our purposes. So when we have Hamiltonian evolution, when we're solving the Hamiltonian equations of motion, there's some conserved quantities. For example, Louisville's theorem states that phase space volume is conserved. But there are also other higher dimensional volumes that are conserved. And all of these are properties of Hamiltonian dynamics. So if we have a cloud of initial conditions in phase space, the volume of that cloud doesn't change. So what is the result of that in practice? So here are these two bottom panels showing you the outer solar system, so sun plus outer planets, using symplectic maps. And we see the correct stable evolution. It's just over 46 periods. And another thing I want to note is the time step is large. This is 100 or 200 days. In the top panels, we reduce the time step by a factor 10 or more. And these are just standard integrators like explicit or implicit Euler. And here we clearly get the wrong behavior. The energy either decreases or increases secularly. So this shows you the power of symplectic codes. This has really allowed us to study dynamics in astrophysics for long timescales. It's what we use in cosmological codes and planetary codes and all kinds of applications. So one thing I worked on is I showed that I looked more closely at this Mercury curve code. It's a function of a critical radius parameter because the critical radius tells us when we're having a close encounter. So this is something that we need to set. And I also presented a symplecticity error. So you can measure your error quantitatively. One way to do this that I did is you consider that you have a map from phase space, so positions and momenta to positions and momenta. We can write a Jacobian of that map, and from that Jacobian, you can make some metric. So for a three-body problem, I showed that for some values of this critical radius, there's a significant symplecticity error. And what does this mean in practice? So for this three-body problem, it should be stable long-term. This translated to an instability. So we're getting a problem that should be stable doesn't look stable anymore. Another significant issue that we might worry about is time reversibility, because Newton's equations are time reversible and time symmetric. So what that means is that if I switch the sign of time, or I switch the sign of the velocities, I should recover the initial conditions. So you can also test the time reversibility of this Mercury code, and you can take large time steps, as large as you want, and you should always recover the initial conditions. I showed that for large time step, you get an increased time reversibility error. And this is what it should look like. So a code that's time reversible should give you an error that's near the machine precision. Okay, and time reversibility is very important. It has a close connection to energy conservation. And energy conservation is related to how well you're solving your problem. Okay, so to solve these issues, we've built a new code called Mercurius, a part of the Rebound integration package, and work led by Hanno Rhein. And we hope that this is going to be a code base that will be useful to astronomers and others interested in planetary dynamics. Here I've just put some recent citations of this code and uses. I've also glossed over some other technical details that I wrote a few papers about, but one issue, for example, is what does it mean to break symplecticity at some points in phase space, and is that important? Another issue is the smoothing function. Mercury depends on a smoothing function, and the question is how smooth you need it to be. Anyway, these are some technical details we don't need to worry about. Some more details about Mercurius. It's built from scratch, independent of Mercury. It solves the same equations of motion, but solves these issues I explained to you, the symplecticity and reversibility issues. So we hope this will be useful to the community. Okay, so I want to change gears and talk to you about numerical chaos, numerical instabilities, which impact our studies of the stability of the solar system. And in particular, Mercury's possible future orbits. Now we're talking about planet Mercury, not the code. So let me give you a brief history of the stability of the solar system. This problem really starts with Kepler's laws. So Kepler states that the planets orbit with perfect regularity on ellipses around the sun. So according to this picture, the solar system is perfectly stable over infinite time. But then we have Newton, who comes up with his universal gravitation. So in this picture, the planets interact with each other, tug on each other. So it's possible for stability to be broken, right? Newton actually personally believed that stability was destroyed, but God intervened to make the solar system stable. So there were some doubts at this point of what really happens. And there were also doubts about whether Newtonian gravity was even correct. Another interesting thing was that Halley used some observations, some ancient observations, to conclude that Jupiter and Saturn must have been at a similar distance from the sun 6 million years ago. So this looks really bad for solar system stability as well. Okay, so the next advances happen about 100 years later with Laplace and Lagrange. So what they decided to do, a simpler problem, is to look at slowly varying quantities. So for example, the planets, their eccentricity or their inclination or semi-major axes vary more slowly than, say, the phases of the orbits. So we can look at how these slowly varying quantities are changing. And we can explore this in a series expansion. So what they showed is that to first order masses in this expansion, these variations in the secular equations vanish. So this is a great sign for stability of the solar system. The picture looks good again. Laplace was also able to explain Ptolemy's observations. And by this point, Newton's gravity was firmly validated. Then we go to Leverrier, and the picture becomes unclear again. Leverrier explored higher order terms that Laplace and Lagrange ignored. And he argued that these extra terms are actually very important. So the Laplace-Lagrange results have only limited application. Okay, so then again, we have some doubts about the stability of the solar system. And Poincaré also did important work on this, showed that no analytic solutions exist to the n-body problem. And Kolmogorov and Arnold showed that under some strict conditions, you can prove the solar system is stable, but those strict conditions don't apply. Okay, so now we go to the present day. And now what we have are digital computers, which finally allow us to solve these equations, both the secular equations and the exact Newtonian equations. In 1989, we have Lescar solves these secular equations on a computer. But also we have the first solutions of Newtonian equations. Just a few planets of the solar system are solved. So it isn't really until 2009. In 2009, we have the first realistic solar system simulation by Lasker and Gastineau. So they do Newtonian gravity, they also do general relativity, and they do some other interesting effects like tides. So one of the things they found, Lasker and Gastineau, is that there's an instability probability of about 1%. So Mercury has a chance of doing something like crashing into the sun or crashing into another planet. Over the next several billion years. So this is quite interesting that there's this chance of instability. But in work we've done this year, we've shown that
how are you defining instability?
Yeah, instability.
Usually how you solve with it, how you define instability. So what are we talking about specifically?
Sure. Yeah, in this case, instability would just be a close encounter of Mercury with, say, the sun or a planet, or some other planets having a close encounter.
That's what's defined as instable.
That's the definition. Okay, so that brings us to the modern day. And we've shown that this work by Lasker and Gastineau and other related works are affected by numerical instability. So it's important to distinguish, is this 1% physical or is this a numerical effect? Okay, so let me demonstrate to you how this happens. In a very simple system, let's take a simple solar system Hamiltonian. We can split it into two pieces. I've just chosen some canonical variables. So the dominant piece is the Keplerian motion. And then we have perturbations on that Keplerian motion, including the interaction Hamiltonian. So the planets tugging on each other. So we have this dominant A function and this perturbation B function. So the way we can solve this is just using techniques from quantum mechanics. You can just create time evolution operators out of A and B. And this is known as the Wisdom-Holman method, which has been very successful in astronomy. So we can create this map like this, these time evolution operators. So B followed by A with, and then B again with these coefficients. And this gives us our solution to the solar system. This is what the basis of what Lasker and Gastineau did and what every other author basically does. So one thing you'll notice, we don't have time in this talk to discuss the origin of chaos, but just in a few sentences. One thing you'll notice is that we've introduced an artificial parameter, h. This is the time step. So we've introduced a new frequency into the system. When you have frequencies, different frequencies in a system, they can have resonances. These resonances have widths, and when these widths overlap, that's actually how chaos starts. That's a whole nother discussion. But the main point is that I've introduced an artificial parameter, this time step, which can lead to this resonance overlap and can lead to artificial chaos and instability. So that's the issue with using numerical methods, is that we may introduce some numerical problems.
Can you go back a second? What are the p's here? The p's in the equations?
Oh, momentum. This is the canonical momentum. I've just chosen some. You can choose many different coordinate systems. And the q's are the associated coordinates. Okay, so let's look at a little bit more how this happens in a real problem. This numerical instability. So this is a picture of the restrict.
So yeah, when you say numerical instability, you mean the same, right? That they're getting close to each other, right?
No, good question. So now I'm using I'm using instability in a different way. Thanks for clarifying that. In this case, it means chaos that didn't exist before. That's what I'm calling instability. I guess there's a lot of ways to think of instability, but I just mean artificial chaos. Thanks for asking.
David, would you say that instability is more like an absorbing barrier? I mean, talking to mathematicians, this is a diffusion process of the eccentricity. And it can touch some boundary. The boundary would be eccentricity of unity or colliding with a planet.
Right.
But it's more of a stochastic process, right?
That's right. So I'm going to show you.
So they can have a physical picture. It's not an exponentially growing quantity.
That's
in
right.
that sort of instabilities.
That's right. Yeah. Not all variables. Some chaos is bounded for some variables. Okay, so let me just show you that this might clarify the picture a little more. This is one of the simplest chaotic problems you can come up with, the restrictive three-body problem. So we have a star and planet on circular motion. So this is in the rotating frame. And we have a test particle, a chaotic test particle with 2 degrees of freedom. Okay, so very simple chaotic problem. There's one conserved quantity, the Jacobi constant. Good. So let's make what are called surface of section out of this problem. Okay, to make a surface of section, you just plot the phase at conjunction. So you plot the phase when test particle and planet here are at conjunction. And on the y-axis is some proxy for the semi-major axis of the test particle. Okay, what this means, we have these dots here. These are called the chaotic C. These are initial conditions that give you chaotic trajectories. These can move around in this chaotic C. Then we have some regular regions. Some initial conditions give you orbits that are not chaotic. Okay, and these are forbidden. The particles can't cross these boundaries. Okay, so what happens when we have numerical instability? We have this case, this unresolved case. And why do I say unresolved? It turns out the important issue is resolving pericenter. So the more eccentric the orbit is, I need to take smaller time steps. And actually you can write a relevant time scale that needs to be resolved. So you need to take about 16 steps. That's a good rule of thumb for this time scale. So that's what I mean by resolved or unresolved. So this is what numerical instability looks like on the right side. So the main idea is that this chaotic region has grown in area, right? Some of these regular invariant curves have been destroyed. There's more which can lead to further instabilities. Okay, so this is what we're talking about with numerical instability. And this is the problem the solar system can have. So we need to watch for numerical instabilities in the solar system. And another important thing is if you're just looking at energy error, this may not show up. This might be a very subtle effect in your simulation. Okay, let's look at this another way. In this case, let's take a simple system. Let's take a sun, Jupiter, and an eccentric Saturn with high eccentricity, like 0.95, and just integrate it for 1,000 years. We're going to use the Wisdom-Holman method, and we're going to use it in various coordinate systems and at different orders. We can make higher order Wisdom-Holman methods. Okay, so the important thing is if we take small time steps, the error is just this typical numerical error, truncation error. But at some point, approximately at this barrier, we get these strange wiggles. These are another way to look at numerical instability. This is the effect of numerical chaos. Okay, and this criteria is given by this time scale I presented here. Okay, so this criteria does pretty well at describing what this is doing. This curve is just another problem, so we can ignore it. Okay, great. So I hope I've convinced you that numerical chaos is a real thing. Let's look at how this might impact the solar system.
But from your picture, you only see that the chaos depends on the time step, right? Or the length of the time step.
Yep. So we're just talking about artificial chaos from this parameter that I introduced, the time step. Okay, so let's talk about the real solar system. This has been explored, like I said, by Laskar and Gastineau, but by other authors as well, that I've listed here. And so what we did is we quantified how much step size chaos they're affected. They're all affected to some degree by step size chaos. And another issue too is the diffusion and slower changing quantities like the eccentricity, which is also affected because it's related to the Lyapunov time. Okay, so let's give an example of how this works. Here's a PDF of Mercury's eccentricity. So the eccentricity of Mercury diffuses slowly in time. Here's a PDF plotted every 250 mega years, which is spreading out. And why do we construct a PDF? Because we're considering a chaotic problem. So that means we need many initial conditions, and that's how we can get a PDF. Okay, what we can do is fit these two parameter Rice functions shown here. These are just Bessel functions. And the two parameters, one describes the centering approximately, and the other one the width of the spectrum. Okay, so what we can do as a first test, these are two data sets, and we're just fitting Rice functions as a function of time. We can see that they're significantly different between one data set, which has a lot of step size chaos, and one that has less. Both the width and the centering are different as a function of time. So here we see one effect. Another thing I want to show you, this is a plot from Abbott et al., where they plotted the instability probability of the solar system as a function of time. And here are the three data sets that I mentioned, that I listed before. This data set here is the one affected most by step size chaos. So we also find it has the highest instability probability. And this red one is least affected. So the question is, what is the true instability of the solar system of Mercury if we can get rid of these numerical effects? And that's what I'm currently working on in collaboration with Sam Hammond and others. So what's Mercury's instability probability if we can eliminate numerical effects? Now, something I want to mention too is step size chaos exists for all kinds of n-body problems, actually should exist for things beyond astrophysics, including dark matter dynamics or stellar clusters and so forth. So it'd be interesting to see how this issue affects other problems and other results. Okay, so for the last part of the talk, I want to switch gears and talk about how geometric numerical integration can help us probe exoplanets. So specifically, I'll just talk to you about one problem, which is the transit timing variation problem. Okay, one of the main ways we detect planets is you stare at a star, and when the planet passes in front of it, you get this dip in brightness. The nature of this dip tells you something about the planet. If this were a perfect, just pure n-body problem, this signal would be periodic in time. But we don't have pure n-body problems. For one, the objects are not point masses. And another thing too is we might have other planets, right? We might have other planets that are affecting the signal, that are affecting the orbit of this planet. So because of that, we get transit timing variations. So here's an example. This timing signal might change in time. And we can actually, this is actually an optimization problem. So the question is, what kind of system can produce such a signal, right? So I can set up additional planets, explore the parameter space, and say which ones are giving me this transit timing signal. Okay, so this approach, the TTV approach, was first used with the system Kepler 19b. Kepler 19b was found to have a transit timing variation amplitude of 5 minutes, and Ballard et al. Inverted this signal to discover a new planet, Kepler 19c. Okay, so you can use geometric numerical integration to approach this problem. And like I said, potentially you have a large parameter space to explore. So if you have a lot of planets, each one has 6 orbital elements and the mass. And so we need to explore this parameter space rapidly and accurately. And throughout the years, I've developed some tools to do this, starting my first paper, and then with Jack Wisdom, we wrote down an efficient Kepler solver. So you also need to solve the Kepler equation quickly. And Walter Denon expanded on this work. Something else you need for any optimization problem are tangent equations. So you also need to write down the Jacobian of your map of phase space onto itself. So that's something we did in work led by Eric Agel. And the tangent equations can help you for many other optimization problems. For example, for studying satellites in the outer solar system, or if you wanted to discover a new planet in the solar system.
Sorry, can you go back another one? So there's a lot of further below. So there's a lot of guessing to find a new planet. Like let's say, I assume there are 2 planets and what the signal should be. Is that the way they discover it?
Yeah, well, I have to explore the parameter space of that planet. And
well, because we don't even know the number of planets.
right, yeah.
So
you may not know the total number of planets.
So it's like a very open universe.
It can be open, but it's usually not that.
How do you claim to like discover a new planet? That's my point. Like you.
Yeah, well, this is what Ballard et al. Did.
Yeah, how did he claim that? Like, how did he manage to claim that? Did he start assuming that there are 3 planets in the system, and if the signal was consistent with that, or what was it that he did in order to do that?
Yeah, just assume there is an extra planet, and actually, I don't know the work exactly, but I assume it's some optimization like I'm talking about to deduce a new planet. Sorry, is that your question?
I guess so. I guess it just seems like a very open problem where you claim to discover a new planet like this. I don't know why are there like 2 more planets or?
Oh yeah, well there could be, and it may not be affecting your signal that much, right? So there could be some other faraway planet, right? So you can't say conclusively this is all there is to the system, right? But you may discover something new.
Yeah, well, I'm just wondering what the standards is are to and what the problem was looked like. But anyway, yeah, go on.
So you're thinking that it could be degenerate, like the solution with 2 planets as opposed to 1? Okay.
I'm just curious of how they do it, like how they do it, and then they claim to discover a new planet. I'm just maybe I'm a little skeptical as well that as to how they claim this because it seems like a very the signal. I don't know if it has enough precision to be able to claim that, but But anyway, good. Go on. Yeah, I'm just curious about what the type of calculations that they're doing.
Well, and we can have other things causing transit timing variations. It's not just other planets, right? Anything that's not point mass and body, any other physics can cause some issue, right? So, okay, so just to show you some work that went into this, to developing the integrator itself, you have to do some careful error analysis, and the tangent equations also involve some algebra and
You're talking about the Jacobian. That was the calculation.
yeah, for the tangent equations. Okay, so let me show you how we might apply this to Trappist-1. So the Trappist-1 system is composed of 7 Earth-sized planets orbiting an ultra-cool dwarf star. This is 12 parsecs away from the sun. And we think 3 planets are in the habitable zone, meaning they might host liquid water. Okay, so I'll just go briefly over this, since this may not be your main interest, but the point is we can solve this optimization problem using symplectic integrators, which explore parameter space quickly. And we can say a lot about the planets. We can deduce their density, planetary densities, and be able to say something about the atmospheres and interiors. And in the follow-up paper, we've done much better, combining new Spitzer data. So the masses and densities are now known to 1 to 8% using this technique. And just for reference, this is within a factor 2 accuracy of the Mercury gravitational parameter known several decades ago. So that's pretty interesting. And we can also start to derive composition hypotheses for the planets. And here's a mass radius diagram of the Trappist-1 planets here, labeled with these letters, A, H, D, E, and so forth. And we can compare it to their solar system planets. These curves are similar to each other. Okay, so great. Let me just get to my conclusions then. I hope I've convinced you that we can use geometric numerical integration, including symplectic and time reversible integration, to help us study the solar system. And I hope I've convinced you that if we're studying the stability of the solar system, this can be affected by numerical chaos, and this affects the instability you might measure. We've also discussed one application of these tools, which is to explore exoplanetary systems like Trappist-1. Okay, thanks for your attention. Okay, pleasure. Questions?
Yeah, there we go, Thomas.
So in the beginning, you said that it's important to have this time reversibility test. How do you design such a test? Do you have an exact solution?
Yeah, well, what you can do is you can see if you can recover the initial conditions. So I can just measure my final state and say how close was it to the initial conditions? Did I recover them? How closely? So I can measure some distance, some phase-based distance.
But the question is, like, you start with initial conditions, then you integrate forward.
Yeah, for an arbitrary time step.
And then you go back with a different time step?
No, so what you can do is switch the sign of time step, for example, or just switch the sign of speeds, of velocities, either one. And take the same time step.
Wouldn't that doesn't give exactly the same? I mean,
No, it doesn't. That's a problem. That's why some codes are not time reversible. So you should get the exact initial conditions, but
Is it because of round off error from the computer, or is it because?
No, this is a much bigger problem than round off. This is at a much greater level. So this is this is when you do the error analysis, it just isn't reversible. It matters. Yeah, it matters what direction you go, forward or backwards.
We're not just making the same calculations as you would when you change the delta t.
Right, like it depends on your starting point, right? So the starting point's different. The initial conditions, like if I'm going backwards, right? The initial conditions are at a forward position. So if you want a reversible system, you'd want your map to depend on initial and final state. That would be a way to make a reversible system. But when it doesn't, that introduces problems. So does that make sense?
Well, I would like to see a mathematical definition, if possible, but.
Yeah, so if you make your integrator symmetrically dependent on initial and final state, that would be an implicit integrator. So you can build an implicit integrator that's reversible. But it doesn't need to be an implicit to be reversible.
Any questions? Any other questions? Yes.
So maybe I'm wrong, but I understood you said new methods may introduce further variables, like computational variables, that finally aim to reduce the overall numerical error of some simulation. But in any case, there will prevail some sort of numerical error that comes from the machine you are using.
Yeah, so we have different sources of error. We have the numerical precision that gives us round off errors. We have truncation error, right? So every method, if it's like a fourth order method or second order method, that means the error scales as time step squared, say. So those are different errors, but there's also numerical chaos. That's a separate source of error. So we have many different sources of error.
Okay, so new methods may introduce new variables, which in turn they will increase new sources of numerical error into the problem we try to solve.
Yeah.
So in which cases would you think it's more relevant for the overall numerical error, the precision of the machine, or in which cases it's more relevant the number of variables of the algorithm we're using?
Oh, yeah. So for all the problems I'm talking about, the precision of the machine isn't important because it's already, you can see here, like about 16 decimals for double precision. So that usually doesn't matter for the test I'm talking about. So numerical chaos would definitely be a bigger effect. But it matters for the problem. What's your dominant error? That depends on the problem you're talking about. Good question.
Have you plan to filter out the numerical chaos? So what's the way of doing that? Like, do you have to just try different methods and then have different simulations, different codes that are able to basically solve the same system and try and figure out what's what? Or
yeah, good question. So the important time scale is this pericentre time scale. And if we take enough steps, like I tried to prove to you here, if we take enough time steps, we'll mute this issue. So the only thing you need to do is for a given, let's say Mercury's eccentricity is growing, you have to adapt the time step and make sure that you're still resolving pericentre. So the way to do it is just to make sure you respect this criteria as a function of time, and that's what we're doing. So I don't think anyone's done that until now.
and so the simulation that Lascar did, was it involving, it was in the solar system that involved planets and asteroids as well? Or?
Yeah, I think Laskar used the 20 most massive asteroids.
Okay.
So yeah,
And the idea would be to do that, but with the eccentricity bound that you propose.
yeah, well, yeah, another thing too is what, your model, like, is it important? Okay, so is numerical chaos more important for Mercury's eccentricity, or are the asteroids more important? And I think the answer is numerical chaos, but I don't think the details, so I don't think necessarily the asteroids are a big effect that we need to worry about, but this is another excellent thing to look at. How precise does your model need to be to get the correct diffusion in eccentricity? That's a separate question. I suspect it doesn't matter much, the model, for Mercury's eccentricity, but it's something that needs to be checked.
How much cost does it? Well, the cost is going to increase if you are going to have to use smaller time steps in order to.
Absolutely, yes.
How much more cost? Even if it's simple, you're talking about like Sun, Mercury system, or what is it? Sun, Mercury, and what? So how much does it? The simplest system involving Mercury, how much cost does it increase computationally?
It's a good question.
Time step.
Yeah, it's a good question. So just to give you some idea, Brown and Ryan, I think, used a time step of around 9 days, or 8.5 days, something like that. And for Mercury's initial eccentricity is 0.2, about 0.2. The correct time step you need is, I think, close to 3.5. So we're decreasing almost a factor, more than a factor 2. So that's approximately twice lower. But as the eccentricity increases, right, like these authors, Brown and Ryan, used a constant time step the whole time. So we'll have to decrease the time step as it goes on. So it'll get even more expensive. So I'm not clear how much more, but definitely more expensive. It's a good question.
Okay, and the final question, when you put relativistic effects, I know that the eccentricities change just a little bit.
Yeah.
Are all these simulations with relativistic effects?
Relativity is extremely important. All of these have some actually different implementations of general relativity. As you might know, you can include more or less post-Newtonian corrections, or you can introduce general relativity as a new potential. There are different ways to model this, but it's very important for the instability probability. It was back. So the last current guess to know 1% probability, that's much higher if you don't include general relativity. And it turns out general relativity has a stabilizing effect.
Oh, stabilizing.
Yeah. That's because it affects the resonances in the system with the pericenter precession. So yeah, it's a very important effect.
Okay, if there are no more questions, we'll end there.